Okay, of course, thank you very much for the invitation. It's really a pleasure to be here. It's a very, very nice conference. And so in my talk, I will talk about something which has a different flavor from what you heard so far. And I hope that you will enjoy it, of course. So the topic of my talk, as the title says, is quantum representation of surface groups, which are some representation of surface groups which comes from TQFT and, oh, louder, okay. So these representations are coming from TQFT, and the goal of this talk, so yeah, before I forgot to say, this is a joint work with Thomas Koberda. And the goal of this talk is to convince you that these representations are interesting and have some exotic properties. So these properties, we'll see that somehow these representations detect simple loops in fundamental groups of surfaces. And maybe the second part, so that would be a big part of this talk. And at the end, we'll see that we can also say something about homology of finite covers using this representation. Okay. So maybe let's start by seeing some properties of this representation. So I'm not going to define you exactly, show you exactly how you can build this representation, but let me show you briefly why they have some interesting properties. So this representation comes from Witten-Reshetikhin-Turaev TQFTs. So a TQFT is a big machinery. It's some kind of functor from a category of cobordism to the category of vector spaces. But what I'm interested in is that, so during all the talk, S will be a surface, compact, connected, oriented, with or without boundary. We're going to suppose that the Euler characteristic of the surface is negative, and let x0 be a point here, and mod 1 S being the group of homeomorphism, the mapping class group of S. So here, mapping class group, I really want the homeomorphism to fix the boundary if the surface has boundary. And I want them also to fix the point x0, and all this is modeled by isotropies. Okay, so what I was saying is that these TQFT are very rich machinery, but what I'm interested in is that when p is an integer, we have actually finite dimensional projective representation of the mapping class group. So here Kp will be during all the talk simply this cyclotomic field. Okay. And dp is of course an integer which depends on p, but it's a polynomial in P. And this number is given by something called the Verlinda formula. Okay. So the matrices become bigger and bigger when P grows. Okay. Okay, so first interesting property. If you take a dent twist, then rho p of t has finite order for all p. Okay. Second property, there exists H, a unitary form defined on the cyclotomic field, preserved by rho p. And this is due to Blanchet, Pierre, Spohm, and Vogel. Another interesting thing is that, yep.
So you say that we have been given some representations, or you are giving the axioms of?
No. So here is the thing. So there is something called Witten-Reshetikhin-Turaev TQFT. Okay? So it's a big machinery, but it produces a lot of things. Okay. But one thing that it produces is this representation. So we have the representation. Yeah. We have these things. Okay. These things are there. So yeah.
We can for each
Sorry?
I'm sorry, we have one for each P?
Yeah. For each integer, we have a representation, a projective finite dimensional representation of the mapping class group.
And for non-integers, there's something else?
No, it's not defined. It's not defined, yeah. And it turns, they're built, they're there, and they satisfy these things. These are not axiom defining it. It was proved that they satisfy this thing. Okay?
So we admit the construction of those?
Yeah. Black box, no worries about the construction. Okay. 3, if P is prime, something special happens. Well, the coefficient of the matrices of rho P are not in the cyclotomic field, but in here, inside the ring of integer of the cyclotomic field. Okay, so these are nice properties, but one remark is that the trivial representation satisfy all these things. Okay, and so if you map your mapping class group to any finite group, and you take a representation of a finite group, you can make it satisfy this thing. So this is not that, although this is very important. So sorry, here this is due to Gilmer. Okay, so theorem, which was proved separately by Louis Founard, Gregor Masbaum. Well, this is not the trivial representation in the sense that the image is infinite if P is big enough. So this is not just a finite quotient of the mapping class group. Okay? And okay, you may say, okay, maybe there is a lot of, so you see that den twist act with finite order, but a den twist in the mapping class group is infinite order. So you may say there is a big loss of information in this story. Okay, if P is fixed, there is some information lost. But there is a very striking theorem, which was proved by Anderson, which says that asymptotically there is no loss of information. What it means is that if phi in the mapping class group is not central, okay, then rho P of phi is not trivial if P is big enough. Okay, so asymptotically there is no loss of information. You get everything, you can know everything. If you know all this representation, you know everything about the mapping class group theoretically with this thing. So how do we get this up? Okay, good. So this thing were known before. So what we did with Thomas Koberda, what I did with Thomas Koberda, is just take this representation for a mapping class group and to make it something for surface groups. And the idea is to use so-called Biermann exact sequence. So you can map, you have this mapping class group. So as it's written there, it's the homeomorphism up to isotopy, but we want the point x0 to be fixed, and also during isotopies. So I can map this in, I can just forget that the point x0 is fixed, okay? And you can check that this map is surjective, and this map is far from being injective. Actually, the kernel is the fundamental group of the surface. So it's a very standard thing, but for those who may not know about this, how to see an element in the kernel here, it's a homeomorphism, which is not trivial, and you cannot find an isotopy to the identity requiring that the isotopy fixes the point x0. But now if you let the point x0 move during the isotopy, it can be mapped to something trivial. So now you just follow the trajectory of x0 during this isotopy, which leads to the identity, and it gives you a loop. And that's the way to see an element in the kernel. And so this exact sequence says that this guy is a normal subgroup of that guy. So what we did is simply we study the restriction of this quantum representation to pi1. Okay. So what can we say? So maybe first theorem. So a theorem which is completely believable when you see all the properties there. So one for all gamma in the pi1 simple. So during all this talk, a simple loop is a loop which is fully homotopy to a loop without self-intersection. Rho p of gamma as finite order. Okay. And second, the image of this is infinite if p is big enough. Okay, so it seems to be clear, or I mean, there is something to prove, but it's reasonable to believe this. And the point is that such representation of surface groups having such properties were not known. So it was asked by Macmillan, who is not here, and Benson Farb to Thomas Koberda to build such representation. And from what I understood, there was a unpublished construction in the case of the one-wall torus given by Ofer-Gaber. Okay, so maybe let me give you the idea of why this is true. Okay, the first step is very trivial. I'm going to give you the full proof of it. So if you see your so take your favorite simple closed loop, and we want to prove that the action by this thing, by the restriction, is finite order. Well, there are two loops, so my base point is here. It's very important. And I have two simple closed curves. Let's say one on the left and one on the right of my loop gamma. And in the Biermann exact sequence, actually gamma is sent to T gamma prime, T gamma twice inverse. And so you see that if the point x0 is here, this product of den twist is non-trivial. But if you take the point up, then these two curves become the same, and this den twist become trivial. This product of den twist become trivial. Okay, so it's really in the kernel of this map. And now, so if you apply rho p to this, this is nothing but two dent twist with two matrices which commute, which has each of them are finite order, so the product has finite order. Okay, very easy. So that was for one. So for
we need the two elements to be communicated.
Sorry?
We need the two elements to commutate so that we have got a finite order.
Yeah, you can make two matrices with finite order multiplied.
If it is not commuted, then it is not finite, right?
It may or it may not be. It depends. Yep.
So it's clear from the proof that the order does not depend on P? Or
The order depends on P. The order depends on P. The order depends on P. And one way to see that the order must depend on P is the asymptotic faithfulness. If there was some, if 10 to the power 10 is always finite order, then it's something which you never see. Okay, so that's a very good point. Yep. And the order actually is P, usually. Okay. 2. So 2, I'm not going to give you the proof. It's called a skein theoretical computation, so it's a little technical, but I'm going to tell you what we prove precisely. So actually, we proved the following. We proved that if gamma in Pi1 is freely homotopic to a figure 8 loop. So I'm going to tell you in a second what is a figure 8 loop. Then rho p of gamma has infinite order for p big enough. Okay, so that will be important in a moment. So let me call this statement star. Okay, so what is a figure 8 loop? Figure 8. So this is nothing but a map from S1 to S with exactly one transverse self intersection. Okay, and also you can look at the image of the loop. So if it has exactly one transverse self-intersection, the image is nothing but a wedge of two circles. And we want this map to be Pi1 injective in the sense that this is injective. So just a picture. So here you have a figure 8 loop, but here, and I messed up. Here, not a figure 8 loop. Here, a figure 8 loop. Okay, this is not Pi1 injective. The image of the graph is a Z, is a copy of Z inside the. Okay. So that's what we prove, and I'm not going to tell you how we prove this, but maybe let's rephrase this theorem in another way. So let me put all this representation in a kind of a big set. So I want to take all the row finite dimensional representation of Pi1 of S such that rho of gamma has finite order for all gamma simple. Okay, you have a lot of representation. Every representation with finite image, to trivial representation, a lot of representation, and I don't care about the dimension. I take all of them. And one way to rephrase the theorem is to say that there exists one representation. I mean, a consequence is there exists one representation here which has infinite image. Okay. Another way to rephrase star is that for every surface S, there exists a representation rho S in RS such that rho V S has infinite curve figure 8. Yep. Okay, so maybe here there is a small thing, this implication, you just have to notice something. Here I say that if you take a figure 8, then it has infinite order for p big enough, but this for p big enough depends on the figure 8 that you've chosen. But there is actually an action of the mapping class group on all this. So if one figure 8 is infinite order, every conjugate has infinite order. And there is only finitely many up to the action of the mapping class group. So this statement makes sense. Okay, so this set actually somehow knows what a figure 8 is. Okay, it distinguished from the other. And so what can we expect to distinguish? Simple closed curve, every simple closed loop has the same behavior with respect to this representation. Everything has finite order. The power of a simple, the square or the cube of a simple loop always has finite order. So we cannot really see them here. So, and here, a figure 8 has some specific property here. But what about other loops which are not powers of simple loops? Can we expect them to be detected by this set? And that's the other theorem. So gamma in pi 1 S not the power of simple if and only if there exists rho gamma into R gamma such that rho gamma has infinite order. Okay. So here you can read this this theorem as a kind of representation theoretical characterization of non-simple closed curve or curves which are not powers of simple. Okay. Any questions so far? Yep.
Why do you take all finite dimensional representation? Like for the moment, everything you said just falls down from the.
So yeah. So. It's just to give a kind of representation theoretical characterization of simple closed curve. Yeah. Okay. Do they have something particular? Yeah.
Sorry. When you say simple, you never consider the boundary curve.
The boundary curve is simple for me.
So it's also finite.
Sorry.
It's also finite order.
It's also finite order. Yeah. Anything which is freely homotopic to a curve without self-intersection. Okay. Okay, and somehow you can think about, and we'll see that this theorem can be made into some kind of algorithm to detect simple closed curve. If you have access to all the finite dimensional representation which satisfy this property, you can detect them. But we'll see in a second that we can make it explicit. Okay, okay, so let's give you an idea of why this thing should work. So, we cannot put this. Yeah, I should have erased it when I was talking. maybe let me keep this thing here. Okay. So let me just give you the idea of why the theorem which is hidden behind is true. So let's start with a loop which is not the power of a simple loop, okay? And let's choose it not to be a figure eight, okay? So for instance, this thing. So you see that here you can see this thing as a map from a wedge of two circles. Okay? You just send this thing here, for instance, and that thing here. Okay? And of course, this is not an embedding at all. But you can choose it such that it's pi1 injective. You can do it. Okay? So imagine for a second that here, so here that's gamma. You can find here a finite cover, so a surface which is like such that this here become an embedding. And here this is a finite. Here this is S. This is some S prime. Okay. Assume this for a second. So because we have done this pi1 injective, here this guy will be actually a figure eight. This gamma here be figure eight. Okay. So here this is not a figure eight, but here this is a figure eight. Okay? Yeah? And so because this is a figure eight, and because I had this kind of family of representation detecting figure eight, I just apply rho of S prime to gamma, but gamma here, and this has infinite rho. Okay, but this is kind of cheating. I'm fixing a surface and I'm fixing a loop, and I want a representation of the pi1 of this surface. Now I kind of change my surface. Okay, so here pi1 rho S prime is a representation of pi1 S prime, which is a finite index subgroup of pi1 S into some kind of GLV. Okay, so well, we do a very easy thing. We induce this representation. This is finite index, so we just make pi1 S acts on the tensor. Let me write it this more explicitly. N G I V G I east of left coset sets of So there is a procedure which is very canonical, very standard. You have a representation of a subgroup. You can induce it on the B group. And the fact that since it's finite index, the induced representation is finite dimensional. Yeah? So let me call this action, let me call it rho. And since we have chosen, we build all this thing with respect to gamma, let me call it rho gamma. And it turns out that induced representation has a very nice property with respect to infinite order, finite order. So rho gamma belongs to RS, and rho gamma of gamma has infinite order. And this is because of this implies this. Okay? Okay, so this is the proof. But the point is that, so everything here seems completely reasonable as standard, except this thing. so this thing, it's not a small exercise to prove this. This is actually due to the fact, so this is, let me write it. This is because pi 1 of S is lerf. So lerf stands for locally extended residually finite. So a group is lerf. There is a definition. I'm not going to write a property with the profinite topology on the group. But something very interesting about this property is that if you take a manifold, let's say simplicial complex, whose fundamental group is lerf, then you can always do this. You can, if a map has some self-intersection, you can actually make it an embedding on a finite cover. Okay? And this is because it's actually a theorem by Peter Scott. Okay. And so that's the proof. And maybe a very last comment about this. Actually, it's a little more than just, as I said, representation theoretical characterization. It's also an algorithm, because here you just need this finite cover. The quantum representation, at some extent, this rho s is explicit. You can compute it. You just need this finite cover. And there is a result by Prem Patel, which actually, if you know some data, very easy data about gamma, you can bound the index of the cover where this is an embedding. Okay? So you just have to search through a finite number of finite index subgroups. And then you can do this procedure. Okay. But this is a little bit cheating because we computed the complexity is like super exponential, something like this. Okay, but it's explicit. Okay. Yeah?
The non-injective cases are easy. Are you saying that?
Sorry? Say
I
it.
mean, you only dealt with pi 1 injective.
Yeah, no, actually, you can make it by one injective over time. If it's not, if yeah, no, okay. You have to take something which is not the power of something else. Okay, and being the power doesn't really, it's not a problem with this thing. Okay, but you're absolutely right. Yeah. So there is actually a bound on the index if you know the word length of gamma with respect to a generating set. I think 16.4, some very explicit numbers. It's maybe not 16, but something very concrete, and which actually doesn't depend on the surface. Okay. Good. Yeah, put my notes. There. Okay, good. So maybe I'm going to use right now a question asked by Christopher, which was why do we use all this representation? And that's true, I'm a TQFT person, and this set of all representations satisfying this property, it's way too big for me. Can we say something at the beginning with just quantum representation? Okay, and can we say something similar to this theorem over there? And actually, there is no result, but there is a conjecture about this. This is called the I mu conjecture, which only talks about quantum representations. Okay, so the conjecture is the following. So it was stated by Anderson, Masboom, and it says the following: if phi, an element of the mapping class group, does not have pseudonus of p's. If and only if rho p of phi has infinite order for p. Okay, so a big problem in TQFT is that this TQFT representation, TQFT invariance, and all these things are built from combinatorial objects.
Sorry, misstated it.
What?
Also not.
Ooh. Sorry. Thank you. Thank you. Thank you very much. I think that's the first time that I said it wrong, but. So these things are built out of combinatorial objects such as Jones polynomial and so on. But at no point in the construction is put anything from hyperbolic geometry. And the big philosophical question is what kind of geometric information we can extract from these quantum objects. And for instance, a question in this philosophy is the famous volume conjecture. So this is something in this philosophy. Can we detect the Nielsen-Thorsten classification throughout the quantum representations? And there is actually a result by Irvin Krah, which actually, so maybe we can ask ourselves what this conjecture says about pi1, representation of surface groups. And so we can actually, because of a result by Irvin Krah, we can restate this, and the conjecture becomes gamma in pi1 not the power of a simple if and only if rho p of gamma has, I mean, the conclusion is the same. Okay. So basically, Krah says exactly what loop are sent to element in the mapping class group with pseudonus of peace. Okay, so as soon as you actually fill a subsurface which is not an annulus, you have a pseudonus of peace. Okay. Good. So now let me tell you some results in this direction. So yeah, this conjecture is still open. So actually, we say that it's 2006, so a good 12 years, and this is still open. And well, that says that to make our algorithm work, we don't need this R as this big set of all representation. We just need quantum representation. So before I talk to you about a result with Julien Marché in this direction, let me introduce some notation. So if I fix rho gamma pi1, I can look at rho p of gamma. I can look at its trace. So I'm sure somebody will see that these are projective representations, so maybe the trace doesn't make any sense, but we can take the trace. It's possible to do something to take the trace, believe me. And so this thing is actually, by definition, since, maybe where is it? Yeah, I mean, these representations have value in the number field. So this is some polynomial, okay, evaluated at exponential 2i pi over p. And qp gamma, so which depends on p and also the loop, this is a polynomial with rational coefficient, by definition of being in a number field, in the cyclotomic field. So I'm going to define rho p zeta p of gamma. Zeta p is another pth primitive root unity. I'm just going to define it by I take this thing here and I plug this primitive root of unity. Of course, it makes totally sense. It doesn't depend on QP of gamma because I've taken a p primitive root of unity. And actually what I'm doing is just I'm applying the Galois group, make the Galois group act on these numbers. That's all I'm doing. Okay, so the point is that this QP is pretty difficult to understand. When P moves, how this thing moves, it's a real mess actually. But our theorem says that asymptotically it's less a mess. Namely, for every loop, the surface, there exists some polynomial. So I have to be careful. This is a capital P, a polynomial with integral, Laurent polynomial with integral coefficient, some finite set in the complex plane, such that if I take the trace, this trace here, I divide by the dimension, okay, which grows like a polynomial in P. This limit, when P goes to infinity and the root of unity goes anywhere actually on the unit circle except this finite set, this converges to. Is it clear? So basically now I have two parameters. I don't have just P. I have P and a P primitive root of unity. So I take these two things and make P goes to infinity. But instead of taking this root of unity which goes to 1, I take a sequence which goes somewhere else, except maybe some finite set of forbidden points. Okay? And I just want to see the limit. Okay? And I claim that the limit is somehow totally encoded in one polynomial which depends only on gamma. Okay? Okay. And so why this polynomial is interesting? Well, if this polynomial is not trivial, in the sense that it's not 0 or plus or minus x power m in C, then rho p of gamma has infinite order for p big enough. Okay, so to prove that a sequence of matrices has infinite order for p big enough is in general difficult. You cannot compute infinitely many matrices. So this theorem says that you just look at this invariant and you check that it's 0 or not. And very good news, it's an invariant which can be computed algorithmically. Okay, so you give me your favorite loop, okay, and by applying some kind of local relation at the self-intersection points, I can compute it in a finite amount of time. Okay, so in this sense, maybe it's a kind of Jones polynomial for pi 1. Because the Jones polynomial is computed the same way, using like local relations on the diagram of a knot. We do it's the same way that we compute it. And so in our work, we actually give a lot of examples, infinitely many examples of loops which are not simple, not power or simple, satisfying this property. And the question, of course, is, can we find gamma not power of simple such that
Question. So
yeah, go ahead.
Who is it?
What?
Yeah.
Yeah. No, it's not an if and only if. Actually, I'm going to ask this question: is it an if and only if? Gamma in 0. And so far we couldn't find any counterexample, of course, otherwise I wouldn't ask this question. And since it's a kind of Jones polynomial, let's say that this question is kind of analogous to know if the Jones polynomial detects the unknot. Okay, some similar question, the level of the pi 1. Okay. So any questions so far? So I'm going to attack the second part of the talk. Yeah.
So this omega gamma finite set, so this is an invariant of the homology class?
Yeah, exactly. So we have, I mean, this invariant is just, yeah, some finite set. And the most important invariant is P gamma. So there are, if you want, two invariants of the homotopy class, a finite set and
why do you need to stay away from that set?
well, the point is that there is one value, namely -1, where there is no way you find this because of some conjecture given by Witten, the Witten asymptotic conjecture. So this is one value which cannot be obtained here. And the other values, we find some kind of limit which looks like what the Witten conjecture states. Okay. Okay. Good. So now, as part, homology finite covers. So I'm going to start with a very elementary question. So you still have your surface, and let me take a finite regular cover. Okay, and let me define H1s of S tilde Z to be the Z module generated by this set. I take all the curves above, simple, which project below two simple closed curves. Okay, it's a big set of simple closed curve, and I take inside the homology above, I take this submodule. And here, let me do S tilde Q. Same thing, but here I start with a Q. Okay. Yeah.
So your H1 of S tilde.
Oh yeah, it's okay. So it's you take all the simple loops above, which project to a simple loop below. Okay, so maybe let me write it again. Sorry about this. C module generated by gamma S tilde gamma simple. Gamma simple. Okay, and so this is H1. And when I put a
What is the P? H1
P is the projection. Okay.
Okay. No, but the H1 exponent
Here?
Yeah.
No, it's a S. No, it's a S. Okay? Yeah? It's fine? Just a notation.
Okay. H1 simple.
Yeah. And, okay. And of course, when I put a Q, I just replace Z by Q everywhere. Okay. So question 1. Can we find a covering such that this is different from this. Okay. Question 2, same thing, but replace Z by Q. So this question actually were asked by a lot of people in a lot of contexts. For instance, Luyenga, Putman, Benson-Farb, Julien Marché also asked this. And for instance, Benson-Farb did a computer program, and for all the covering that the computer could compute, there was always equality here, never different from. Okay? So maybe without writing, let me just talk about the motivation given by Andy Putman. So from a paper by Putman and Whelan, they proved that if this never happens in Q, there is always equality, then a question raised by Ivanov as a positive answer. What question? Every finite index subgroup of the mapping class group has a finite abinization. Okay, so it's a question. People refer it as computation of the virtual first Betti number of the mapping class group. Okay. Okay. So also without writing, let me or maybe let me write this one. So what is known about this? So there is a theorem by Putman and Einstein, which says that if the surface has at least one boundary component, then the question Q2 has a positive answer. Okay, but they couldn't do the question Q1, Q2 for closed surface is still open. And what we proved, actually our theorem was before the theorem. As Q1, yes, we can find example for Q1, but we don't know about Q2. It's still open. Okay. Okay, so maybe let me give you the idea how we can build such example. Was talking about quantum representation of surface group. What does it have to do with the finite cover of surfaces? So here, oh, perfect, it's written here. This representation, okay, so if P is prime, this representation land into some, the coefficient land into the integral points of the number field. Okay? And when you have integral points, you can do very nice thing. For instance, if you go in Z, you can map Z into Z over N for all N. And you can play the same game here. So maybe let me call this rho P here. And here you can map this into one minus exponential pi for P power N plus 1. So N is an integer. Okay, so you just kill powers of this thing, bigger powers. And it turns out this is a finite group. Okay? And so now, what is a map from pi 1 to a finite group? It's just a finite regular cover, SPN S. And so here, what we have, since, let me write it here. So we have SP0, SP1. Since we're modding out by bigger power of this element, we have actually built a tower of covers. Okay, and at the end we have SP infinity. Pi 1 of SP infinity will just be the kernel of the representation. Okay, and let's suppose that rho p of pi 1 is infinite for a second. Okay, so we have a tower of covering where the index is bigger and bigger. What we proved, now we can erase this part. Theorem S. We proved that the index of this thing S, so here I should put SPN. So let's see this problem through this tower of covering. We prove that this index is at least P over this one. Okay, so you fix P and you make n goes to infinity, and this thing becomes bigger and bigger, goes to infinity. So it's not, this cannot equal this. So this, let's say, covers which comes from TQFT give you are some exertive covers in the sense that they satisfy this property, which is absolutely not explicit. We have to go very far to get this kind of covers. And I think I'm